So moving over to Canvas on the 3.3 page, we are going to start by downloading the starter file, which should look something like this. Data transformation starter. And then we can navigate to our tutorial by clicking this link here. And it should look something like this. So a brief overview of what we're going to cover in this section. So we are talking about data transformation now. So in the previous tutorial, we learned about visualization, which is one of the latter parts of the analysis process. So typically before we get to the visualization, we have to do some data cleaning. We have to work with the data, transform it, tidy it, import it. That's what we're going to be studying in this tutorial. And the main package that we're going to be using is called dplyr, which is again from the tidyverse. So a few readings, we are going to be following along with chapter 4 of R for Data Science. So if you want more written out explanations and more examples, please refer to this, as well as the dplyr help documentation. Very good resource, and the cheat sheets as well. Prerequisites. So what we need is the tidyverse installed, and then we also need the Laman package installed. So this is where our data set comes from. So install this package and then get that loaded by running library. And then once you have those, you should be good to go. So let's start with the basics. So throughout this section, we're going to introduce lots and lots of dplyr functions that are going to perform those big picture data transformations like filtering, organizing, creating new columns. All those things that we can do manually in Excel, we're going to do via functions in R. And each of these functions has their particulars, of course, but they all have a very general setup, the same setup because they're from the tidyverse. So what that setup is that our first argument is always going to be a data frame. And this is going to be very handy when we are using pipes. So that's something that we're going to talk about very soon. And then after the data frame argument, you are going to have arguments that operate on the columns, and we use those column names without quotes. And then the output of our function is always going to be a data frame or a tibble, which is another kind of data frame. So we're going to chain functions together. And so we're starting with the data frame and ending with the data frame, which is going to be a very useful aspect of these functions. So let's actually talk about the difference between these two types of data that we're going to work with. The first one is called a data frame. This is what we have been using. This is what the iris data set is. And all of the functions we use were perfectly fine with data frames, but there is a special kind of data frame in the tidyverse known as a tibble, which just has some nicer printing properties than a regular data frame. So to try that out, let's take a look in the console, these two different data sets. So if I just type in iris, right, it prints out really, really ugly. Or I have to like scroll through this, all this nastiness. That is because printing has not very good, data frames don't have very good printing features. Instead, tibbles, on the other hand, which is what the diamonds data set is that we worked a lot with last tutorial, is a tibble, and it prints very, very nicely. So in order to get this same kind of output from a data frame, I have to use glimpse, and then I can type in iris, and then I get this output. So by default, tibbles just have nicer printing properties. That's the main advantage. So we're going to use our example data set, and we're going to turn it into a tibble so that we can get these nicer properties. So let's go ahead and take a look. So it also shows us the column types. We've seen that before with the diamonds data set. But first, let's talk about piping. So this is going to be a very, very popular technique that we're going to introduce now, and it's a way to combine functions together. So typically in programming or in algebra, we nest functions together. So by doing this, we're doing f of x. So f parentheses x. So an example of this is, let's say I generate some numbers from a normal distribution, and I want to scale them. So I want to standardize them. So easy enough, when I standardize these, I'm turning these all from x values into z-scores. So I have a bunch of z-scores now, but let's say I now want to find the standard deviation of the z-scores. I have to wrap that first argument around with my new function. This is called nesting. So we're kind of working outwards. So my standard deviation is now 1, which makes sense. Standard deviation of a standard normal is always going to be 1. This can get confusing, especially if I have 3 or 4 functions. Kind of trying to work outwards can get very confusing. Instead, a more readable way is going to be with the pipe. So there's 2 pipes. There is this pipe, which is the percent, the greater than, and then percent. This is the one that I will be using. It's from the Magritter package, which is going to be something that we can configure. But there's also a base R pipe, which is going to be this one down here. So there is a slight difference between the two. I prefer this one. We're not going to talk about why, but both of these are going to work the exact same for our purposes. So what this does is it takes our first argument and passes it and then to the function. So that's how we read this, x and then function f. So if I have this same random normal sample and I want to pipe it to the function scale, take x and then scale it, I now have my z-scores. Now when I want to get the standard deviation, I just chain it together. I just chain these functions. And then I get my same output as 1. So this is a much more human readable version than this one. So this is the way we're going to work with all these dplyr functions, is using piping. And that's what I expect you guys to do as well. So let's take a look now at our example data set. So we're going to use the batting data set from the Laman package, which contains Major League Baseball data from 1871 up to the present season. And here's a preview. So we get a player ID, the year that they started, the stint, team ID, league ID, games, and a bunch of other stats. So lots and lots of baseball statistics. Hopefully you are somewhat familiar with baseball. If not, you will be after this. And because we're going to be working with a lot of data on this tutorial, we want to turn this batting data set into a table so we get that nice printing features. So the way that we're going to do that is we're going to use a new object and call it batting with a lowercase b so that we don't overwrite the original. So once you have that Laman package installed, we can just run batting, and we're going to use as_tibble capital batting. So if you're following along in the starter file, we will type this in our code chunk. And all that does is save a new object now as a tibble. So if I were to check the class of my lowercase batting, I should get a TBL DF, which is a tibble data frame. Whereas if I check the class of capital B batting, it is going to be just a regular data frame. So in all of the following notes, we need to refer to this data set as lowercase b batting in order for this tutorial to work on the back end. And we're going to run one more line in the console or in your starter file. We're going to run batting, chain that to select dash concatenate, which is the C function, and then these two variables separated by a colon. So we're going to learn exactly what this does, but if you want to copy that line and paste it into your console, I've already run this, so it doesn't exist right now, but it would work for you because you haven't run that yet. So we are going to have just this subset of the column. So we're going to learn what that means. So goal for this tutorial, which we will come back to at the end for the application, is going to be to recreate a few plots, just like we did in the first one, except now we're going to be focusing on the data transformations to get those plots. So suppose we are interested in the relationship between several batting statistics, such as home runs, runs batted in, which is RBIs, etc. for the best home run hitters. The specific questions that we can answer depend on how we have the data structured. In other words, what each row represents. So currently, if we take a look at our example data set, each row represents a single player for a single season for a single team. So we have player level data at the season level. So for each season. So we can only answer questions that are based on season. I can't answer how many home runs does this player have in their entire career based on the current setup. One question I could answer with the current format is how many games were needed for the best 100 home run hitting seasons of all time. So this is the 100 best seasons of all time, and plotted on the x-axis is how many games were needed. So we see for the very best, it was about 152, something like that, whereas all these other ones needed above 160 games. And that's the type of question that we can answer with the current setup. But one thing that I could learn, that I could investigate, is career level data for a particular player. So Ken Griffey Jr., I'm from Cincinnati, so a famous Reds player. So how was his career by season? How many home runs did he hit every single season versus the games that he played? So there's a lot of data scenes that happen behind the scenes for this, but our output is a line plot for the home runs each season, and we fit a smooth curve to it. And it's also shaded by how many games he played. So maybe down here in these low seasons, right, he didn't play many games, so maybe he got injured. Whereas up here, he was healthy and playing a lot of games and in his prime. We could also ask questions about the best home run hitters overall for their careers. And that's what's plotted in the second visual. So this is the 500 top home run hitter players. And it's also colored by whether or not they're still playing or not. So if we think about the data that is behind the scenes, I have to check whether or not they're still playing. So whether or not they played in 2022. And I also have to sum up all of the home runs that they have. Same thing for Ken Griffey. I need to sum up all of the home runs per season, right? That's the data that we're going to focus on. And then I also have to filter to just Ken Griffey Jr. Those are the things that we're going to learn how to do in this tutorial. So the first thing that we're going to do is start with a function called select. A lot of times with data, we're not worried about every single column. We just want to focus on a subset of the columns. So to do that, we need to have a way to eliminate columns that we don't want. In other words, only keep the columns that we need. So to do that, we can first get a list of the column names. So by running col names on our data set, I have a list of all of the possible column names. And we want to select just the columns that we need. So we're going to have a few different examples, the ways that these can be done. So the first, we'll run select. Remember, with all these functions, the first argument is a data frame or a tibble. So I have select, batting, comma, and then now I'm going to operate on the columns. So let's say I want to select player ID, year ID, home runs, and I can run that. I just get a data frame with these columns. I can also do this with piping. So what if I wanted to do select, and then I could do either the base R pipe or the McGritter pipe. I'm going to use this one. I could use select, pass that. Nope, I got it backwards. I got to start with my data frame, pass that to the function, and then I could do player ID, year ID, and home runs. And that would give me the same result. So kind of what's happening here in this select statement is the batting is kind of implicitly being transferred into this first argument. So I could kind of reference that by using a period. And when I run that, I get the same thing as well. So my batting is being transferred. It's being passed, chained, piped into select as the first argument, but that is implicitly happening, so that's why we can ignore it. So that's why we don't have to write that. But there is a few other ways that we can use this select function and reference the columns that we need. So first one is by selecting all columns from a block. So if I know how my columns are organized, then I can use batting. I can pipe it into my select statement, and then I can do player ID colon at bats. So this is going to get me, if I take a look at the original data set, this is going to give me everything from player ID to at bats, all of these organized in a block. So when I run that, it gets me all of those columns from player ID all the way in order to at bats. We could also take out columns. So far I've just been naming columns that I want. I could also name columns that I want to remove. So we could do that. I have a few different select statements already set up for us. To do that, there's a few different ways, but we need to put these in a vector. So we use a named vector of the variables. So concatenate, let's say I want to use the same. Now I want to take out all of those first variables. So take these out. What we have to do is just specify an exclamation mark in front of our vector of column names. So in computer science, a exclamation mark is read as not. So this is select not everything from player ID to at bats. I could also do the same thing, but instead of an exclamation mark, I could use a minus sign, and that's going to give me the same result. If you know where your columns are at in terms of their position, so this is the first column, player ID. This is the second column, year ID. Stint is the third column. We can also specify by the position number. So I could do select, not concatenate, first column, fifth column, for example, and the seventh column. So run these. These first two should give me the same results. Looks like it did. And then I took out the first column, I took out the third column, and the seventh column. So a few different ways to do this. We can also combine all these different methods. So I can take some out, I can keep some, I can use them in a block, I can specify their column numbers. All of those are legal. And that is what we can show here. In addition, we can recognize that the order of our variables is going to be how they are selected. So if I do select 1 to 4, so I'm going to get the first 4 columns, but I'm going to take out year ID from those first 4. Then I'm going to have concatenate, home run, and at bats. And when I'm specifying these, I actually don't even need the concatenate. I can just specify them like usual. When I run this, I'm going to get player ID, stint, and team ID, which is part of the first 4, but I took out year, and then I have home run and at bats. If I switch this, so if I switch it from at bats and home runs, my result is going to have these flipped. So the order that you specify them in the select is going to be the order of the final result. And then we can also rename columns using select. So the way we do that is select new var equals old var. So note that all variables are not included, will be dropped. So to do this one, let's say I want to rename the games column to games. So currently it is G, but I want to rename it to games. So to do that, new variable name, old variable name. And we just get the new column, and that's it. So we only keep the ones that are explicitly mentioned. which could be a downside. And if I only want to rename a few columns, we can use a different function that is going to be in the next section. So that is kind of the select basics. So we can also talk about the advanced way to use select, and this requires a few different helper functions. So helper functions are functions that we're going to be using within my select statement to help us pick out the columns that we want to keep or take away. This can be useful because if you have, let's say, 100 columns, if they all have a specific naming structure, it's going to be a lot easier to use these helper functions than to try to pick out the organization or explicitly name, right, 50 different columns. So that's when these helper functions are helpful. So first one that we're going to have here, let me comment these out so I can run just these first lines, is the where. So I'm going to select batting where. This is helpful when we just want to get data of a certain type. So I only want to get my numeric variables now. So I'm going to do where parentheses is numeric. So this is going to select all columns that meet this condition. My condition is numeric. So now I'm getting just the numeric columns. It took out that league ID, took out the player ID. I could also do is.character or is.factor. And now I'm just getting my character variables, and it looks like the only one is player ID. So that's one way that we can do these helper functions. Another way is very helpful if you know that there's a similar data pattern for all of the variables, how they're named. So let's say I want to, there's player ID, league ID, and year ID. Let's say I want to get all of those because they end in ID. I want to get all of those kind of categorical informations. So we could use ends with. So select all variables that end with the pattern ID, and we specify that in quotes. When I run that, I get my player ID, year ID, team ID, and league ID. So that's very helpful. There's also starts with, so anything that starts with a pattern or anything that contains. So a few different options that we have. None of those other ones are applicable for the data that we have right now, but those could be useful in the future. The next helper functions are useful when you have a vector of column names. So if you have a character vector, maybe you did some functions before and you have now your output is going to be a vector of column names that we want to work with. To select them, right, typically I have been using all of my names without quotes, right? In all of these statements here, I've been specifying the column names without any quotes. So if I want to use this directly, I can't just do select vars. That should potentially, live coding, give me an error or at least a warning, because what it wants me to do is use these all of or any of functions. So what these do are select properly these functions, these columns from my data frame. And there's a slight difference between the two. So all of will throw an error if there is a column name that isn't there. So let's say I don't have a batting average column, so BA, or maybe I misspelled one in my character vector when I was typing it out. When I live code this, hopefully it'll throw an error because of the way that all of works. So I get an error. If I change this to any of, this allows for these missing columns and doesn't give me an error. So typically it's safer to use any of, but that is going to be the difference between these two functions. So there is an exercise for us to try. So next up is going to be renaming columns. So renaming columns This is when we want to keep all of our variables, but just rename a few of them. So to do this is rename new var equals old var. So very simple. We could use batting. I could pipe it to rename. And let's say I want to rename doubles, which is the X to B, and triples, which is the X 3B. So notice here that contextually, this would be 2B, so starts with a number, which is not a valid name in R. Everything has to start with a letter. I could get around that, so maybe I wanted to name this. So first, let me just run this, make sure this works. So here, I get doubles, and I get triples instead of X2B and X3B. Let's say I wanted this for some reason to start with 2B. When I run this, it gives me an error because this isn't a valid name. So what I can do to get around that is by specifying these backticks around my invalid column name. And now I have the column name as 2B. This is kind of bad practice, right? This is how I can get column names that are ugly like this. Things with spaces in them, especially when you read in data from Excel. This is going to be a bad way to name variables. We always want to use what's called snake case, where we have underscores in between everything. And then I don't need to use these backticks. So that's just best practice for naming. Might be a bit cumbersome to type out, but just results in a lot simpler, a lot easier code for us. So there is an exercise for us to try. So let's go ahead and stop right there for this video, and we will pick up with relocating columns in the next one.